This diagram maps a common distributed architecture. Multiple microservices wired directly into separate database nodes to read and write data. When developers write raw database code repeatedly, warning indicators populate, revealing duplicated query logic, redundant authorization, and isolated index management inside every codebase. This fragmentation creates significant operational risk. When persistence is implemented inconsistently across an ecosystem, security protocols drift over time. The codebase becomes brittle, and the maintenance burden on developers scales with every new service added. Centralized data governance fails in this environment. Strict compliance requirements, like marking personally identifiable information or executing GDPR data deletions, easily fall through the cracks because there is no standardized layer to enforce them. Direct database access compromises operational safety. Relying on individual teams to independently execute persistence logic breaks auditing mechanisms and introduces security vulnerabilities at scale. Platformization solves this fragmentation. It takes decentralized, shared infrastructure behaviors and snaps them into a strict, unified architecture, so all services operate consistently. Inside the Nile ecosystem, this philosophy is enforced by the Simple Data Layer, or SDL. It acts as the core persistence abstraction component. SDL replaces service-specific schemas with a document-oriented persistence model. The central layer intercepts raw data from services and formats it as structured documents. Developers manipulate domain entities via standardized APIs. All requests route exclusively through this hub, which independently handles storage routing. By standardizing the persistence workflow, SDL shifts developer focus back to executing business logic. The underlying platform handles distributed data governance. To function efficiently without breaking external systems, SDL enforces a strict decoupling between what a client sees and how data is stored. This splits the data entity. The left node is the contract representation, the external API. Isolated on the right is the domain representation, the internal document model for storage. This separation enables schema evolution. The internal domain expands for new data, while the external contract remains strictly stable. Downstream client APIs continue functioning exactly as before. The external contract shields them from internal structural modifications. Decoupling the contract from the domain removes operational friction. Services evolve internal logic without triggering system-wide data migrations. By funneling all data mutations through a single abstraction, SDL acts as a mandatory checkpoint, enforcing platform security and data compliance policies. Tracing a query into the SDL pipeline, it hits an authorization constraint gate comparing credentials against tenant identifiers. Unauthorized queries are rejected, preventing destructive updates. Approved requests pass to a PII handling gate, where sensitive fields receive field-level encryption for strict GDPR compliance. Embedding governance directly into the persistence abstraction ensures compliance is enforced at the storage level, removing the risk of developer oversight. Standard CRUD operations are effective for individual entities, but they fail when systems attempt to update thousands of records simultaneously due to network overhead. Look at this high-latency loop, a microservice fetching thousands of records, modifying them, and writing them back. SDL replaces this with bulk patch by filter. A single command executes, applying updates directly inside the storage layer, completely bypassing the network fetch. This capability allows platforms to efficiently execute system-wide mutations, such as flipping feature flags across a tenant or asynchronously correcting corrupted datasets. Executing bulk operations directly at the storage layer protects network bandwidth and prevents API throttling during system-wide data migrations. In a concurrent distributed system, conflicting writes and lost updates present a constant threat to data integrity. SDL manages concurrent transactions using optimistic locking and semantic constraints. When two conflicting update requests attempt to modify the same document simultaneously, one succeeds while the other is safely blocked to prevent data corruption. Beyond state mutation, SDL manages state removal. Executing hard deletes risks permanent data loss. To prevent this, SDL utilizes soft delete. Deleted documents move into an isolated trash bin sector. A background time-to-live countdown timer then runs, executing automated removal only when it expires. By enforcing native concurrency controls and soft delete lifecycles, SDL ensures that human error or system race conditions do not result in unrecoverable data loss. In a distributed platform, writing data to disk is rarely the end of a transaction. Downstream systems must react to those state changes. SDL automates this process. Whenever an entity undergoes a lifecycle action, the layer emits a domain event, pushing an outward radiating automated payload. The layer monitors 4 triggers: create, update, delete, and restore. Each generates distinct event signals routing to downstream system nodes. These automated events drive audit pipelines and trigger event-driven workflows across the network without requiring additional microservice logic. By automatically broadcasting guaranteed state changes, SDL operates as the reliable source of truth powering the asynchronous microservice Meta system. Let's review the end-to-end lifecycle of a persistent mutation within the Nile ecosystem. This maps the end-to-end process. An external API request enters as a contract representation, transforming into internal business logic. The payload then enters the centralized SDL block, sequentially lighting up internal modules, triggering auth constraints, optimistic locking, and event emissions before resting in document storage. This unbroken chain of governance relies on one absolute platform rule: microservices must never directly access the database. The simple data layer abstracts persistence complexity to provide the structural foundation for operational safety, high-scale performance, and strict governance across the enterprise ecosystem.